Hi, I'm Noeline Prince, and today we're going to be talking about Parkinson's disease. A disclaimer, I am not a medical doctor, and this is not meant for diagnosis or for a medical audience. This is mainly for research engineers and scientists who are trying to find alternatives to pharmacological treatments. Right. So, what is Parkinson's disease? This is a neurodegenerative disease, which means it's characterized by the degeneration of the neurons. It's progressive, and as far as we know, it's irreversible. The associated motor symptoms are first, muscle rigidity or stiffness. Basically, this is an increased resistance to passive movements. There are two types of rigidity that comes. One's called the cogwheel and the other is the lead pipe rigidity. Secondly, bradykinesia, in other words, slowness of movements, decreased spontaneous movements such as eye blinking, swallowing, and arm swing. Thirdly, tremors. So when we talk about tremors, these are mainly occurring at rest. So when you start moving, you don't have these tremors. All three of these are early features of Parkinson. The last two that I have shown are more late features of Parkinson. And the first out of that is the postural change. You have a flex posture, postural instability. Maybe you can have falls. And then finally, gait disturbances, such as shuffling or lack of swing, arm swing when one walks. Just a very brief history about Parkinson's disease. This was first discovered by James Parkinson. He was reported this in his essay on shaking palsy in 1817. Then in 1861, it was discovered that Parkinson's and tremors had distinct characteristics, that they're not the same. In 1865 is when the name Parkinson's disease was coined. From 1879 onwards, there were a lot of pharmacological treatments, lots and lots of stuff. And what's interesting for me is the deep brain stimulation. It started, I think, in 1987. The publication came out in 1989 that deep brain stimulation, or DBS, reduces the symptoms of tremor in Parkinson. Currently, there are a lot of other therapies also. They're trying to do gene therapy, MPTP treated animals are used for a lot of Parkinson studies also. Right. In the first video, we talked about the anatomy of the basal ganglia. I talked about the structure of the basal ganglia, the caudate and the putamen, which make up the striatum, then the globus pallidus, external and internal segments, the subthalamic nucleus, and the substantia nigra, pars reticulata, and pars compacta. Then we talked about the direct pathway of the basal ganglia. We said from the motor cortex through the striatum, the GPI and SNR are activated, which in turn reduces the inhibition of the thalamus, which excites the motor cortex. Also talked about the indirect pathway from the motor cortex to the striatum, and it goes to the GPI and SNR through the GP and STN. So these are what we call the direct and indirect pathways of the basal ganglia. Then we talked about the role of the substantia nigra, pars compacta. We said that the striatum had both D1 and D2 receptors, which are dopamine receptor subtypes, which are either activated or deactivated based on the pathway. And we also said that in Parkinsonian conditions, the dopamine is less, and these pathways are They're not able to activate or deactivate these pathways. Right. So today I'm going to talk a little bit more about these structures, which can be a little bit confusing because these are not found in textbooks. This research is currently being done. So I have kind of summarized 2 papers. There's a lot more to it. Again, I have simplified this as much as possible. So we start off with the basal ganglia. We talked about the motor cortex, and I'm going to add the brainstem and the spinal cord over here. So first off, the change I'm going to do for the thalamus is I'm going to add some nuclei of the thalamus. First, I'm going to make a distinction between the ventral anterior nucleus of the thalamus and the ventrolateral nucleus. Then I'm also going to add 2 more nuclei, centromedian nucleus of the thalamus and the parafascicular nucleus of the thalamus. So CMPF will be added. Now I'm going to add 3 more structures, 3 more targets that recently generated interest in Parkinson. First is the pedunculopontine nucleus, which is found in the upper pons over here. I'm going to put it as PPN in blue. Second is the superior colliculus, also found in the rostral midbrain. And finally, the lateral habenula, which is located in the dorsomedial surface of the thalamus. Right. Now that we know where these structures are, let's go back to our functional circuitry. So we have the thalamus, the VAVL, CMPF, and I'm going to add these 3 structures. Right. Now let's talk about the circuitry. So first, we talked about the projections. I'm going to add a new projection from the motor cortex to the brainstem and to the STN, and also from the PPN to the brainstem and spinal cord. Earlier, we talked about the direct pathways from the motor cortex through the striatum to the GPI and SNR. Then we talked about the indirect pathway from the GPE and STN up to here. Here's where things get a little bit different. We're also going to have more projections from the GPE to the GPI and SNR, as well as reverse connections from the STN to the GPE and from the GPE to the striatum. Now we talked about the projections from the basal ganglia to the thalamus, which remains as the same, but we also have projections for the CMPF. From these structures, you have connections to the motor cortex, which excite it and make us to be able to walk. But you also have projections back from the motor cortex to the thalamus, as well as from the thalamus to the striatum. Hang in there with me. We're getting to the interesting part of the recently developed research. So the output of the basal ganglia, which is given from the GPI and the SNR, it's found that there are projections, mainly inhibitory projections from these structures to the PPN, SC, and the lateral habenula. One more connection before we end, and that is from the PPN to the STN and from the STN to the PPN. That's pretty much the circuitry that we have. And lastly, I talked about it last time, the striatum has dopamine receptors, and the STN projects to the striatum, the D1 to the, which are excitatory connections to the direct pathway, and D2 inhibitory connections to the indirect pathway. So this is the overall connections. And now, because we need to know how these connections are different in Parkinson, I'm going to change the thickness of these arrows to correspond with their presumed activity. So in the normal connections, or normal scenario, you will have connections like this. In the Parkinsonian connections, what's going to happen is these strong connections are going to go weak and certain other connections are more predominant. So this is the situation in Parkinson. I'm not going to go into detail about how this stops movement, but it is interesting to notice that the symptoms due to these altered connections that I have shown are both for the motor as well as the cognitive symptoms of Parkinson. And as mentioned, the dopamine is reduced from the SNC. If you want to read in detail, I have given these two research papers that you can go and look into, and they have explained it pretty well. So to kind of summarize about the treatment of Parkinson, first and foremost, in any of these, care and help for families and education is very much needed. You have a lot of assistive technology. Two of my groups in the engineering faculty have developed several devices. And if you Google search, there are many assistive technologies available to help cope with the day-to-day activities, the daily activities that are required to do with Parkinson. You also have pharmacological treatments. Every year, the research comes out with different treatments available. We also have surgical treatments. You can remove parts of the brain that we think are responsible for certain activities, for either excitatory pathways or inhibitory pathways. This is not used as much now, but this is pretty much how we started. You would either burn a certain section of the brain or you would remove a certain section of the brain, and the person still would be fine. As I mentioned at the beginning, a lot of gene therapy is happening. And then finally, the area of interest to me, deep brain stimulation. What we do is we try to find the targets that are responsible for the altering of different pathways, and we try to alter the pathways the way we want to. So that brings us to the end of this video, and I hope that this was helpful to you. Thank you very much.